Hello, everyone. Welcome you back to study MA4822, which is a course about the measurement and the sensing system. Today, we move on to study the lecture on measurement of a visual signal. As usual, before we enter the study of today's lecture, let me give you a quick review or overview about the answer to these 4 questions. Question number 1, why to study this course? Question number 2, how to study this course? Question number 3, what are you going to learn from this course? And question number 4, how to learn the knowledge from this course. So let me start with the review of the answer to the first question, which is about why to study this course. And now you know that our mission on Earth include number 1, to understand the world through the discovery of knowledge. Number 2 is to improve the world through the invention of a smart product, smart machine, and the smart system. Then how to discover knowledge? The answer is to have a sensory data. Then how to obtain sensory data? The answer is to make use of measurement and the sensing system. Then how to invent a smart product, smart machine, and the smart system? The answer is to incorporate a closed-loop feedback control system into the design of a smart product, smart machine, and the smart system. Then what is a closed-loop feedback control system? The answer is it is a system which consists of 3 basic modules or 3 basic building blocks. One of them is a sensor, right? And in future, you may see the presence of smart parking system, smart street lighting system, smart building system, smart home system, smart environmental system, smart health care system, etc. in the city. And the future city may also include Internet of Things. And you know that one of the 2 basic devices inside Internet of Things is a sensor. So therefore, this course is very important. Then the second question is about how to study this course. My advice to you is to put yourself into the mindset of a designer. Then with the keyword of a design and the designer, automatically you will ask yourself these 4 questions. Who are the user? What are the needs of the user? What should be the functionality of the product or system that you are going to develop in order to meet the need of this user? And what should be the solution behind the design of your future system or product in terms of a sensor, Internet of a sensor, or measurement and the sensing system, right? So the answer to the first question is obvious to you because user include ourselves, smart product, smart machine, and the smart system, right? Answer to the question number 2 is also obvious to you because all these users have the common need, which is to have a sensory data, right? Then answer to the question number 3 depends on the nature of a user. For example, smart vehicle may need a certain type of a sensor, and the smart robot may need to have another type of a sensor, right? And the answer to question number 4 is to study well this course. At the end of the study of this course, you will know the solution behind the design of your future product or future system in terms of a sensor or measurement and the sensing system. All right. Question number 3 that you may have in mind is about what are you going to study from this course. Basically, this course will cover the study of the physical principle behind the design of these popular sensor in electric domain, in mechanic domain, in environmental system, and in intelligence system. In addition, this course also teach you the detail, basic detail about the physical world, the basic detail about the conceptual world, and this course also teach you the basic knowledge for you to cope with the randomness in the physical world and for you to understand the fuzziness in the conceptual world, right? Then the first question that you have in mind is about how to learn the knowledge from this course. The answer is learn the knowledge to guide the design of measurement and the sensing system. The design will involve 2 steps. Step number 1 is to convert value of a physical quantity on the measurement into readable value. And the step number 2 is to do calibration, right? And for step number 1, in general, you may face these 2 situations. The first one corresponds to the case in which it is good enough for you to make use of a front-end sensing element in order to transform the value on the measurement into computer readable value, all right? However, in most cases, you may encounter the second situation in which you have to make use of a series of at least 2 sensing elements, right? In order to transform the value of the physical quantity on the measurement into readable value, all right? Then the purpose of a calibration is for you to obtain the output, which will be exactly equal to the input. In addition, the unit of a measurement assigned to the output will be the same as the unit of a measurement from the physical quantity on the measurement at the input, right? So that is a basic guideline for you to follow in order to apply learned knowledge from this course. Okay, now we are ready to move on to study today's lecture. Then you will see today's lecture is about the measurement of the last physical quantity under consideration in this course. And this last one is the most important one, because inside human intelligence, the major pillar is visual intelligence, right? The second major pillar is auditory intelligence, or intelligence which leverage on the use of sound or voice or speech, right? But visual intelligence is the major, is the number 1 pillar underlying human intelligence and also machine intelligence. You just imagine, without the audio signal, we are not able to communicate among ourselves, all right? But at least we can see. But what happens if there's no visual signal? Then we can see nothing. We cannot see each other, and even eventually we cannot see anything in the physical world. Then our life will be meaningless. Understand? If we can see nothing, it means what? Your life is meaningless, right? So you will see visual signal and acoustic signal are the 2 major input to human intelligence system and also to machines intelligence system. All right. So therefore, these 2 type of visual signal, or the 2 type of signal, are extremely important to the development or design of intelligent system, intelligent machine, or intelligent product, etc. Right? So then in today's lecture, we will study the basic physics behind visual signal, and then we look at the computational aspect, okay, of a visual signal. In particular, we try to know, okay, what could we compute from the visual signal, and then you will know that the computation in terms of geometry is quite complicated. This is why we are going to spend additional 2 lectures to study computational aspect with the use of visual signal. Then today we just focus on the measurement of intensity and the chrominance inside visual signal. Then for geometrical information, how to compute or determine geometry from visual signal, we will study this aspect in subsequent 2 lecture, right? And before we enter the study of the section, which is about the visual signal, it is interesting for you to see this short video. Okay, so basically this video telling you that the seeing is not believing. All right, so you must do practice with whatever you have learned. All right, so at the end of this lecture we will show you some practice with MATLAB. So it is a good news because you have a free access to MATLAB. Then with MATLAB and your laptop computer or desktop computer, actually you have a vision system. All right, then here I'm going to showing you some example source program for you to do self-practice. All right, so let's start with basic physics behind visual signal. All right, so this video showing you that it is very important for us to have a visible visual signal. Then in this way, we know each other, we can see each other, we can see the environment, all right? And in particular, we can interact among ourselves or interact with the robot, etc., right? This is a typical example of a visual signal enabling the interaction, all right? So without the visual signal, it's not possible for us to undertake such interaction. All right. And then in this case, you see, without the visual signal, it is not possible for us to undertake this type of operation. Pick and place, pick and place. You need to see where to pick. You need to see where to place because pick location is not fixed. Place location is not fixed. All right. So you need to use the eye to measure the position. All right. Then it's very important for us to know some visual intelligence, visual signal so important to us. And then what is the nature of visual signal? Actually, visual signal here means visible light. All right. Then you want to know, okay, what is the origin of the light? So actually, you will see inside the atom we have an electron. When electron move from a high energy orbit to lower energy orbit, then there's a release of the energy in the form of a photon. So that is the origin of the light, okay, or origin of the visible light, right? Because there is a release of energy in the form of light, okay? So when electron inside atom loss, okay, energy, but this process is reversible, right? So the reverse process is to capture the light and release the electron, because when the electron captures the light, okay, then its energy level increase. When the energy level increase exceeds certain level, certain value, then the electron could, okay, become a free moving electron. All right. Later on, we'll come back to this aspect. We call this is the photoelectric effect. Okay. So due to this photoelectric effect, then we can emit the light or use the light to release the electron in order to produce a current. All right. So this is a physical phenomenon, and this is the origin of emission of the light. Right. Then here is one more example. Then you see we can, okay, develop a light source, okay, to let the electron get to release the light in big quantity. So this slide basically help you to understand this phenomenon. Then we can apply this phenomenon to develop, okay, or design or invent lighting device, something like that. All right, okay. So based on this phenomenon, then for the object which will continuously emit the light, then we call this entity as a light source. Okay, so it's like acoustic signal. So there's a source for acoustic signal, and then there's a receiver for acoustic signal, and then there's a path for acoustic signal. Then for visual signal, the situation is the same. Okay, we must consider the source of a visual signal, the receiver of a visual signal and the path of a visual signal. All right. So now you understand in the physical world, we have an entity which will serve as a light source. All right. Okay. And then we need to understand the property of the light. Okay. The first property of the light for you to remember is the type of path. So actually light will travel along a straight line. Light will never travel along a circular path, all right? Within the same media, that means in air, okay? If there's no other media, okay, to change the direction of travel, then the light will continue the travel along a straight line, okay? So this is a first property for you to know about the light. Light means what? A stream of photon. It's like a current. Current is what? A stream of electron. The light is a stream of photon. That's it. All right. And when light travel in one media and encounter another media, then two things will occur. One is refraction, another is refraction. Okay. So first look at the refraction, okay? Depends on the property of the interface between two media, okay? If the interface is very smooth and shiny, then refraction will occur. For example, if you have a mirror, okay, when light hit the mirror, then 100% will be 100%, okay, refract, okay, in another direction, okay? And here is a property. So we'll have an incoming light, then this is a refracted light, okay? And the incoming angle, and this is refracted angle, all right? So this is a property for you to remember that the I is equal to R. That means the incoming angle is equal to the the angle of a refraction, okay? And they are symmetric about the normal vector, okay? Perpendicular to the interface between the two media, all right? So this is a property for you to know. And then we can make use of this property, okay? Because the incident, the angle of incidence and the angle of refractions are equal about the normal axis, normal vector, okay? Perpendicular to the local surface of between the two media. So then in this case, if let's say we have this surface in the shape of parabola, right? Then we place light source and this is a focal point, is a special point there, okay? Particular point. Then you will see all the reflected light will become parallel, okay? So then we can use this property to design a lighting device, okay, to illuminate a large area, okay? So outdoor, something like that. All right. So this is a property for you to know. And here's one more example. You see, so we have an incoming light ray and reflected light ray. Then you will see the angle of incidence is equal to the angle of reflection. All right. So this we also call it angle of incidence. Then this is the angle of reflection, right? So they are equal, okay? So this is a property for you to remember. Firstly, you will see, okay, if we place the light source here, then the outgoing light will be parallel. Reversely, if the incoming light are parallel, then the reflected light will all pass through this point. And in optics, we call this point as a focal point of this parabolic mirror. And then the distance between this point and this point, we call it as a focal length. Now you start to encounter some technical term, okay, used in optics. And also you see another technical term, which is called as a principal axis, right? So you see when light coming through here, so basically we will pass through the focal point without deviation and straight, then okay, continue, and here you will hit the surface, all right? So that is a special light path. So we call it as a principal axis, right? And the second phenomenon is refraction. Then you may say, what happens if the light can enter the second media? Then you will see when you enter the second media means what? The density of these two media are different. If they say the density of these two media are the same, then you should not consider you have a two media, they are the same. Okay, when we have a two media means density of these two media are not the same. All right. Then when the light enter a media with a higher density, then you will see the angle of refraction will be smaller than the angle of incidence, right? So this is the angle of incidence. Now you see this term here, angle of incidence. This is the angle of refraction, right? So when the density of a second media is higher, then angle of refraction is smaller than the angle of incidence, right? Then you may ask this question, how come like this? So actually, with your background, it's quite easier to understand now, okay? When the media density is higher, then resistance is higher, something like that, all right? So then just imagine you have a vehicle, all right? This is like incoming light ray, okay? Then the left view will start to receive resistance first, okay? Before the right view. Then this difference of timing will make the light to change the direction, all right? And it will change direction, make the angle of refraction become smaller because the light has a tendency to become perpendicular to the surface, all right? So this is why you see this phenomenon, okay? Then reversely, if let's say the second media has a smaller density, then the angle of refraction will become bigger, all right? So it makes sense, John, all right? This is a verification element. This is glass, okay? In the form of there's a rectangular rod, all right? So then you see this is the incoming light. Some of them will be reflect, okay? And some of them will enter, okay, due to refraction. Then you see angle of incidence is larger than the angle of refraction. Then from first media to second media, because now second media has a smaller density. Now you see angle of refraction will be bigger, larger than the angle of incidence, right? But since this media is the same as this one, and the change variation of angle are the same, then you will see once the light enters the air again, it will restore its orientation back to the original one. So this is why then you see parallel line, okay, come out. Okay, so this phenomenon, all right? Okay, so we know, okay, we have a light source. Then we want to know, is there any light receiver? Actually, the answer is yes. Like every one of us has two eyes or not. Our eye are the receiver. It's like the case with acoustic signal. We have a two ear. Our ear are the receiver of acoustic signal. Then in this case, our eye are the receiver of visual signal, right? So the light can enter our eye, then we can perceive, right, the light ray. And then here, this is a direct perception. And here is indirect perception. So you will see, if we just look down in this direction, and this is a river, lake, or something like that, then due to the Miller effect, okay, and we may perceive object like this, okay? So we see the image of this object, right? But actually inside the eye, we see the tree is upside down inside the water, right? So this is a phenomenon. And I guess every one of you have such experience, all right? It's quite easier for you to verify with your eye, right? And here is one more example. If they say the real object is here, then we place the two mirror. If our eye look in this direction, actually we will have an impression that this object is not here, is here, right? So it's because our eye interpret the light in the normal way, okay? So when our eye interpret the incoming light, basically we will, okay, interpret it that all this light come from here, and actually light come from here, right? So this is the illusion okay, due to our vision. And again, this help you to understand this statement. Seeing is not believing. This is one more example, okay? So when you see object is here, you should not believe that the object is at the image 2. Wrong, object is here. Even it's not at the image 1, object is here. So again, so this slide help you to understand this statement, seeing is not believing. You must do practice, you must verify, right? Then here's one more example. You see what's going on inside our magic eye, right? So you discover our eye has this optical device here, and the lens incoming light will be focused on a small tiny area, all right? So here is upside down, and all this signal eventually will be converted into electric pulse inside certain area of our brain for processing, all right? So this will inspire us to design camera or machine eye or electronic eye, all right? So that is a hardware aspect of measurement and the sensing system for visual signal, right? So immediately you know we need to have at least we call it as a lens. We need to have a lens. Then we need to have a casing. Then we need to have a matrix of sensor to convert the light, okay, signal into electric signal, right? So already from this slide, or more or less, you start to understand, okay, what should be the major component, okay, inside the design of a measurement and a sensing system for visual signal, right? And here is for those of you, like if you wear a glass, right? And for whatever reason, let's say, then we have far-sightedness, okay, we have the problem of focusing the incoming light at the right location here, because you see, okay, this is after rectification. You may have this situation, let's say we focus, our eye focus the image here, then we must do rectification, or too near, you see, we focus the image here, then we must aid the lens to bring it back to the right position. So this is help you to understand, okay, our lens is not perfect, and sometimes we need to do the rectification, and in order to have a clear vision, right? So I guess some of you may have such a problem, right? Okay. Then you will see that device is quite important. Then how to design such a device? Okay. So here is first design option. All right. For example, we want to make the light, incoming light, okay, from a small area and to become outgoing light, which will enter larger space. You will see, let's say these are the incoming light, then this is the outgoing light. So you will see incoming light come from this small area, and the outgoing light will go to a larger area. Okay, so this is one scenario. If we design optic device, okay, or glass in this way, so basically on the left hand side we have a spheric surface, okay, so which is concave. On the right hand side we have another spheric surface which is also concave, right? So then we have a concave lens. Such device is called as a lens, or we call it as a negative lens. Okay, negative lens is to amplify, okay, the space occupied by incoming light. Okay, then from here you will see this one has a certain application, right? If they say the observe the area is too small, then okay, then we need to amplify the space occupied by the light ray. However, okay, if they say machine is small and the physical space is large, that is in normal case. Our body is small, our eye is small, all right? How to make a small device to observe an area, right? That should not be this one, because we need to reduce the dimension of the incoming light into a smaller area, so that we can use our small eye to perceive a large area, right? So Then this negative lens, you can do experiment. Okay, this picture basically showing you the experimental result. So you see incoming light from a smaller area, then outgoing light will go into a larger area. Okay, so this is a typical scenario for us to amplify the space occupied by the light ray, right? But in most cases, this is one more illustration, right? If our eye is here, then we will see this is the black one is a real object. Then image seen is okay. So we can see its image. Okay, so this is another illustration, right? Okay. So you will see the incoming line in the smaller area, then outgoing line covers the entire area here. Okay, so you can imagine this is just a tiny space there. Then you use this lens, and eventually you can see more detail. All right, okay, something like that. But however, in our case, our eyes are small, and we face a larger physical space. That is the normal situation. Then in this case, we just design this positive lens or convex lens. All right, so you will see left-hand side we have a spherical surface. Okay, like this. This is a convex. And the right-hand side, we also have a spherical surface, which is also convex. Then we create such a device. Then the property of this device is to reduce the dimension of the incoming light into a smaller area. Therefore, we can use our small eye to see a larger space. All right, so this is an application with this type of positive lens, and actually inside our eye, the lens of our eye actually is a positive lens. Okay, it's not negative lens. All right, and this is an experiment to verify. Okay, you see the incoming light in larger area, the outgoing light in a smaller area. Then we can put the small sensor to be there to convert light signal into visual signal, something like that. All right. So then you will see the lens inside our eye basically is a positive lens, right? So you see the lens is here. Iris is a device to control the amount of light which can enter our eye, all right? And then we have a large object, then we have a smaller image here, all right? Then this is a property of positive lens, right? But actually you can also use this one to amplify smaller object. All right, so you see when the position of the object is smaller, that means this is the focal length enter here. Now you see this is a small object, then the large image. If we put our eye here, then we will see enlarge the image. All right, so that means positive lens has at least two properties. All right, so if we place object very close to the lens, then we have this amplification effect. All right. Okay, so this is just for you to know. Then we want to answer this question now. Okay, how to capture incoming light, and in order to form an image by machine, then we can imitate this design of, okay, we just imitate the design of a human eye, because the human eye is being designed this way. Then we just imitate. Okay, we have a positive lens. Then here, okay, we put the object here. Then we have the casing of the camera or electronic eye. Then you will see image will be formed. Okay, inside the camera. All right, so for you to know, and actually we apply this result to guide the design of a measurement and the sensing system for visual signal. Right, and this is a one more property for you to know, because here is the property about geometry channel. Light pass through straight line, change the direction, hit here. So all this concern geometry. Then there's another important knowledge, okay, encoded inside the light, which is about the intensity and the color, and we call it as a coherence, right? And there's an important discovery by scientists in maybe a few hundred years ago. Okay, so we observe that when light pass through a glass prism, then you will see this is a colorless light. Then it become a colorful light, right? So and then we understand because the wavelength of all these component color are different. All right. So therefore, and their angle of refraction are different because angle of refraction is a function of wavelength. Then this is why we can do the color separation. Then you see colorless light then become a colorful light. However, 2,500 years ago, Buddha already noticed and made this statement: colorless is colorful, while colorful is colorless. Right? So you see, the history of a science is very, very short compared with the history of a religion. Then you see a lot of discovery have already been made in the study of religion, right? For example, this phenomena. So 2,500 years ago, Buddha know this already, right? So then he made this statement, right? So it's surprising, right? So then why there's a separation of the color? Reason is because of wavelength dictate the amount of angle of refraction. Okay, so you will see longer the wavelength, shorter the angle, smaller the angle of refraction. Then for shorter wavelength, then larger the angle of refraction. Right? Okay, since the light basically is what? Is electromagnetic wave with the frequency and the wavelength. Then you remember when we do the study about the measurement of acoustic signal, etc., and we see this Doppler effect. So actually, Doppler effect also apply to the light. All right. When the light source approach us, then the wavelengths tend to increase. Or the wavelengths become longer, and frequency will frequency will become higher, wavelength will become shorter when the light source approaches us. Then the light source receding us, okay, move away from us, then the wavelengths will increase, frequency will shorten, and this is why when we see the light tend to become reddish, so it means what? Everything try to move away from us, something like that. All right. So this is a application, okay, with Doppler effect in order to interpret this situation. So when object move away from us, then the light turn to become reddish. All right. Okay, something like that. All right. And, background knowledge for you to know is about this phenomenon of color, right? So color basically is our physiological or psychological sensation inside human mind. Then we may ask this question: okay, will animal see the same color as a human being see them, right? So for example, we see this is a red color, whereas a cat also perceive this signal as a red color. We do not know, right? So this is a question for you to know that eye can only perceive visible light, and the visible light is a very narrow interval, okay, in the whole spectrum of wavelengths or frequency. So you see, we can only see light, okay, with the wavelengths vary from roughly 400 nanometer to 700 nanometer. So that is a range. Okay, beyond range, our eye cannot see them. Again, this is another way to interpret this statement. Colorless is colorful, while colorful is colorless. Okay, so colorless means we see nothing, emptiness. When we see nothing, does not mean there's no light, because we have invisible light channel. Okay, so all these are the light channel, right? So it means when we see colorless means empty, nothing, right? So it does not mean there's no color. They still have a light there. So this is another way for you to interpret this discovery 2,500 years ago, right? Okay. And another useful knowledge for you to know is about this property of having primary color. So this property tells us that any color could be the sum or weight in the sum of these three primary color, RGB, All right, so we will use this property to guide the design of electronic eye in order to produce color image, right? So this is also very important property for use, okay, in order to design measurement and the sensing system for visual signal, right? So then you will see if we put the RGB together with the same weightage, result is what? White color, right? If we mix the red color with the green color, we have a yellow one. If we mix the blue color with the red color one, we have a magenta color. If we mix the blue color with the green color, then we have a cyan color, all right? So this is the result for us to produce by adding these three component color together in different with the different weightage, and then we can produce all kinds of color. So eventually we can reproduce all kinds of color. All right, okay. Color is an electromagnetic wave. Then we can modulate, is amplitude, modulate is a frequency. Or you use the light wave to modulate the carrier signal's amplitude, the carrier signal frequency, and then to support communication. Understand? Because we have studied this aspect in the previous lecture about the modulation, making use of acoustic signal, right, and a carrier signal. So we use acoustic signals amplitude or frequency to modulate carrier signals amplitude or frequency. And in a similar way, so we can use light signal or visual signal to modulate the carrier signals amplitude and the frequency, right? So in order to support communication, and you may see in future, okay, all the vehicles could communicate among themselves when they turn on the light and making use of the light signal or visual to undertake communication among the vehicle in the nearby, right? Okay, so that's about the basic physics behind the visual signal. Now we look at the aspect of doing computation with visual signal, and you will understand computation with a visual signal is extremely complicated, right? Spend another 2 lectures to study the computation of geometric information from a visual signal. Then for this lecture, we only focus on the computation of chrominance intensity or the conversion of color from one space to another space, etc. All right, because for intensity, chrominance is quite straightforward because color is a vector of 3 components. That's it. Okay, then we can transform the color vector from one space to another space. All right. So once you have a vector, you can calculate what is the length of this vector. The length of this vector is just equal to intensity. All right. Then once you transform it into LAB color space, and then AB coordinate indicate the color information or chrominance. Right. So for chrominance information is quite straightforward, so we will study them in this lecture. Then for geometry related computation, we need to spend 2 more lectures in order to understand the working principle. All right, so you see, it is not so simple, okay, with computation of visual. Right. So first question that you may have in mind is about what to compute from the light. So actually, we can compute geometric parameter from the light, and the geometric parameter basically include path and the direction, right? And the second category of knowledge, okay, which could be computed from visual signal are photometric parameter. And the photometric parameter basically means luminance and chrominance. Luminance is related to the energy level, so we call it as intensity, and chrominance is related to frequency, a psychological sensation, right? So then we call it as a color. So color basically is a physical quantity which are related to the wavelength and the frequency, right? The intensity is a physical quantity related to the magnitude of light intensity, the light signal or visual signal, right? Or amount of photon inside the stream of light, right? Something like that. Then the path direction should be complicated, all right? So then with the use of a path and the direction, we should be able to perceive the complex geometry from the environment. So this is why we need to spend another 2 lectures in order to study the way to do the computation of the geometry from visual signal, right? So what is the path of a visual signal? So basically, we know that the light will travel in space by following a straight line. Unless you hit an object, then the reflection will occur, and the reflection will occur, something like that. Then how to handle such a complex situation? Because we may have many reflection of the point there, etc. All right. So this is one aspect about the geometry of a visual signal. So path basically refer to the spatial location traveled by the light ray. All right. So then here you see 2 examples with a negative lens. So you see this is a light source. Okay, light emit out, then enter this glass. All right. Then there's a reflection plus a refraction. Then refraction, then exit from here. There is outgoing light. Then you see the change of the path. All right. There's a visual signal. So when the visual signal travel within the same media flow as time, and that's when the interface between 2 media, then refraction occurs and the refraction occurs, etc. So you see, this is an example with a mirror, perfect mirror. Then we only have refraction, all right? So the angle of incidence is equal to the angle of refraction, all right? Then when the light can enter into the second media, if there's a second media has a higher density, then you will see the angle of refraction will be smaller than the angle of incidence, right? So these are the phenomenon of a change of direction of the path by the light, right? Then in terms of geometry, this is a basic equation of a thin lens, right? So for the positive lens, then if let's say we have this focal lens, this is the distance between the focal point and the center of the lens. Then we have object distance, the distance to object. So this is the distance from this lens to the object. The S2 is the distance to image. Image is behind, so this is the distance from the lens to the image, right? So then 1 over S1 plus 1 over S2 equal to 1 over F. So this is the thin lens equation, right? So this is a basic equation which determine the geometric property of thin lens. And actually, the most important property for us to use in the subsequent 2 lecture is this property based on the thin lens. So you will know that when the light coming out from this point travel in this direction, which will pass through the center of this lens, then he will continue the journey without changing the direction until he hit the image plane. So this property is very important, okay? So subsequently, we will just use this property, right? So because here, you look at so many triangles here, so basically it helps you to understand this equation. And the one way to interpret this equation is to say that the light pass through the center of the lens, so it will continue the journey until you will hit the image. That's it, all right? And actually, this property is quite full, okay, for us to determine the 2D geometry and the 3D geometry, etc. All right, so we will come back to the use of this property in the subsequent 2 lectures, all right? And this thin lens also applicable to the situation when the distance to object is smaller than focal length. You will see this is the S1 is the distance to the object. So S1 is smaller than F, all right? And this equation is still whole, is still true, right? So this, and actually we can make use of this arrangement to come out the design of this product. This is called microscope. Then from here, is small, init is larger. So this is the way for us to see a small object, okay? Because we can produce a large image of a small object, right? So then this animation help you to understand that. Okay, if there's position eye here, okay, so when the object is, then you will see the interpretation by our eye here. Okay, will be the image which is larger than the object. All right. So you see this property, when light pass through the center of lens, it will continue the journey, right? Another property is when you have a light coming parallel here, then actually it will pass through the focal point. Okay, if incoming light is parallel to the optical axis, this is optical axis. Now you see virtual image is larger than the object. Okay, so this is a working principle of a microscope, right? So another property for you to remember is about this optical axis. Optical axis is always perpendicular to this surface and also pass through the center of the lens. If the light coming from here, it will pass through, okay, pass through the lens. All right, so this is also another property for you to know, right? Okay, so that's about the geometry, because anyway, we'll come back to the study of measurement of geometry with the use of visual signal, right? Then for this lecture, we focus on luminance and chrominance. What is luminance? Luminance basically represents the energy level of the light ray, because the light is what a flow of electron. Electron is what is a carrier of energy, because when electron lost energy, then photon. Okay, light is a stream of a photon. Sorry, is a stream of a photon, and the photon is a carrier of energy, because when electron lost energy, then it will emit the photon. So light is a stream of photon, and the photon is a carrier of energy. Then in the incoming light, you may have a density of a photon. Then such a density is being measured by intensity, right? So here you see, if you have a higher density of a photon, then higher energy. If you have a lower density of photon inside the incoming light, have a lower energy, right? So, and what is chrominance? Chrominance basically is a parameter which indicate the value of wavelengths and the frequency, because the visual signal or stream or the movement of a photon basically follow a sine wave. So you have A sine omega t plus B. So omega basically has a frequency. So chrominance basically indicates the value of omega or 2 pi f, the f frequency or wavelength, because they are related anyway. All right. So that is the chrominance. So you see, we must measure energy related physical quantity and also frequency related quantity. Right. So chrominance is a kind of a measurement of frequency. Intensity or luminance is a kind of a measurement of energy, right? So then in this case, you remember any color is the weighted sum of a 3 primary color. That conclusion gives us indication about the color space. And then what is a color space? Color space should be a 3-dimensional space, right? Because any color could be the weighted sum of a 3 primary color. Then we can use this 3 primary color to form a color space. Then any color is a point inside the space. So therefore, then we have this idea of a color space, right? So, and inside the color space, basically, we know the distribution of luminance, chrominance of distribution of chrominance of incoming light. We can describe their distribution inside the color space, right? So then, okay, by default, you understand we have a RGB color space. Then you may ask this question: is it this unique color space? So actually, it's not, because mathematically we can transform a 3-dimensional space into another 3-dimensional space. Then there's an international organization which hire many scientists to do the experiment. Then based on the experimental result, then we discover there are additional 2 special color space. One is suitable for measurement, another is suitable for display or visualization, right? Like the photo and the video and film, okay, and etc. Right. So for us, our concern is measurement. So then, but anyway, it's good for us to know these two additional color space, right? So this is RGB color space. Then you will see the presence of chrominance at the different location inside this color space, and also the energy level. You see white color is here, so energy level is high here. Then dark here, that means this is the energy level close to 0, right? Something like that, right? And this is the LAB color space. This space is very useful for us to use in order to do the measurement of intensity and chrominance, right? So you see this color space has a separation, okay, between intensity and the chrominance. I or L, this is the L axis. L indicates the level of energy, and the AB indicates the value of frequency, all right, or the color length or chrominance of incoming line, right? So you see we use two coordinate AB. You see when A is big is a red, okay, when B is big is tend to be yellow, all right, blue, okay, here is negative B, all right. Then negative A indicate more or less a green color or something like that, right? Okay. Then white color is here, dark color is here, or black color is here, all right? So, okay. Then HSV is useful for display visualization, right? So then we have a hash indicates the color angle. Then you see when hash change, then the sensation of a color change, the green, blue, red, something like that, all right? Then S is a saturation. That means how green it is the color, how blue is the color, how red is the color. So it's an indication of a saturation. S is in this direction, all right? And V is a brightness, basically it's an energy level, all right? So, and here is a dark, you can say dark blue and the bright blue, all right? So V will tell you dark blue, white blue or something like that, okay? So this is a more intuitive to for visualization, all right, okay. Then how to do the conversion. So this is a basic computation of, which are related to the use of visual signal, right? Okay, so, and there's no mathematical proof because this is the result obtained by experiment, okay? Through an intensive experiment, we discover these two additional color space. Then how to convert RGB into LAB. So these are the formula for you to use, okay? RGB times this constant matrix, get the 3 intermediate value X, Y, Z. Then you apply X, Y, Z to calculate LAB. Then here, how to get the Y max, X max, the Z max. So you just supply the R max, G max, and the B max, all right? To get the X max, Y max, and the Z max, all right? So these are the solution for you to, right? How to convert RGB color space to HSV color space. Then this is the formula for you to follow, okay? So get the maximum value from these 3, minimum value from these 3. Then C is equal to the difference between maximum and the minimum one. S is equal to the ratio between the difference between maximum one, minimum one divided by maximum value, right? V is equal to the maximum one. Hash is calculated with this equation, depends on the value of M, all right? If M is come from red color, then you use this one. If M come from green color, use this one. If M come from blue color, then you use this equation, right? So this is a formula discovered by extensive experiment, right? Okay. About the computation with the visual signal, as I said that we are going to spend another 2 lectures to study computation of geometric information from visual signal, right? So then for this lecture, it's good enough for us to know how to compute chrominance intensity of color, right? Then the next issue will be how to do direct measurement of visual signal, right? So that should be the major focus, okay, of our study here, right? So then you may ask this question, why do we need to do measurement of visual signal? And the answer is, well, there are many applications, right? For example, lighting control, Okay, there's a smart street light team control system. So we need to have a measurement and a sensing system for visual signal trauma. All right, and communication. If let's say we want to use a light to do communication, then we need to capture the light. Okay, and do the modulation and the demodulation in order to derive the information. All right, and in particular, there are a lot of automation and interaction in the physical world involve heavy use of a visual signal. For example, without the visual signal, we cannot see each other, we cannot interact among ourselves. All right, so but with the use of a visual signal, we can do a lot of things such as measurement, inspection, surveillance, guidance, recording, learning, interaction. Without the visual signal, we cannot read the screen channel. We cannot watch the lecture video. We cannot attend the tutorial channel. All right, and we cannot read the books channel, read the report or read the article, etc. So you see, learning heavily depends on the use of a visual signal. All right, so there are many reasons for us to believe that the capability of making use of a visual signal has the #1 importance to humans' intelligence and the machines' intelligence. All right, okay. Then here is an example which make use of visual signal to do the measurement in order to guide the robot to do the pick and place. Right. And one more example of making use of a visual signal to do the measurement in order to know the profile of machined part. Right. And then we can verify whether the dimension of all these objects conform to the design specification or not. All right, so it's quite easier for you to understand the usefulness with a visual signal and the #1 importance of a visual signal to human intelligence as well as to machine intelligence. All right, then next question is, what is the principle for us to follow in order to guide the design of a measurement and a sensing system of a visual system? The answer is to imitate human eye. That's it. All right. Then when we analyze the human eye, let me discover basically the transformation incoming light to the internal electric signal involve these steps. First, light into optic image, then convert optic image into analog image. Then convert analog image into time function of a voltage in series. You see, in the human eye, we have a nervous system. Okay, so then the information could be sent to the brain. Okay, area, brains, different area. Okay, in series, right? So these are the major steps involved in the design of human eye. So therefore, we just follow similar principle. Then from here, you will see we have an incoming light. Now we know we have an optical lens. Okay, then we can convert incoming light into optical image. Then we need to know how to convert the photon into electron, because the photon is being created by electron. Okay, then it travel in the space everywhere. All right. The electron. Then we need to convert electron, receive the photon. We need to convert photon back to electron, then produce a voltage, right? So the good news is we have such a photoelectric effect. Okay, material. For example, we have a photodiode, or we have this Morse capacitor. Okay, photosensitive capacitor, something like that. All right. So therefore, once we have an optic image, then we can convert photon into electron. Okay, then we can read out the electron, okay, in series, then produce a time function. So that is a principle. So once we have a series in time function, then good news is we can apply controller to convert time function of the voltage into digital number. And you see AD converter. AD converter basically is a built-in module inside microcontroller. Once we have a digital image, then we can use all kinds of software to undertake image processing, etc. All right, so these are the principles for us to follow. So basically, this slide summarizes Now we zoom into the detail now. Okay, so first question is how to implement such a principle in order to come out the direct measurement of visual signal. All right, so here we leverage on this important result which says that all microcontrollers are programmable digital sensor of voltage. Therefore, if we can convert incoming light into voltage, then done already, right? So then we can leverage on the microcontroller's capability to convert voltage into digital number, right? So then in this case, we just need to add in 3 additional modules, okay, to microcontroller. Then we will get the solution for us to do the measurement and the sensing of a visual signal. The first module is to convert, okay, incoming light into optic image. Second module is to convert optic image into analog image. And the third module is to convert analog image, because analog image is a 2-dimensional matrix of charges, okay, into time function of a voltage. This is a third module, okay, analog image to time function conversion. Then here we have a time function of a voltage in series. Then this will be the input to microcontroller. All right. So now we look at the detail into these 3 additional, okay, module. So the next question is how to convert light into optic images. The answer is straightforward because we know we have a positive lens, all right, or convex lens, all right. So let me just design such a device that has a lens, has a housing or casing, all right. Then this is very simple, just a positive lens, all right. So once you have an object here, the image will appear here, okay. So it's something like this, okay, illustration. So we have a lens, we have a key, okay, it's an object. Then this object will form an image in this 2-dimensional space, like in this plane. All right, that's it. All right, so this is answer to the first question. Second question, then how to convert optic image into analog image? Then we split the answer into 2 steps. First step is to know how to convert light intensity at one point into analog voltage. If we are able to do one single point, convert into a voltage, then if you have a matrix of point, then just have matrix of such device. So the good news is to make use of photosensitive diode or photosensitive capacitor, all right? So this is an example of a photodiode, all right? Photodiode basically implements a reverse process of producing photon from electron. Then this one is to produce electron or release electron from photon, okay? So that means when the electron capture the energy from a photon, then its level of energy increase. When the level of increase exceeds certain level, then this electron could escape from the atom and then enter into the conductor and then move freely, build up the charge. All right. So then we can design such a device called the photodiode. Then you see inside the photodiode, we have a P-type of silicon. P-type silicon means this silicon can receive electron, has a location reserved for electron, okay, have a seat for electron to come in, right? So, okay, so this is a P-type. N-type silicon means what is due to the dopage, okay, we dop the other atom inside. So that means this is a silicon which is ready to receive a positive charge, okay? Positive charge, yeah. This is a P-type means is a silicon which is ready to receive a negative charge like electron, right? So then when the light come in, then a lot of electron feel excited, then it become a free electron. Then all the free electron, you see, will concentrate here because this is a P-type. A P-type is a silicon which is ready to receive a lot of electron. Then you see electron all will appear there. All this negative charge, we call this is a charge. All right. So then after that, we can ship this charge out, okay? Then become the output, then become the voltage, become the signal to the microcontroller, right? So, and then, okay, then how to ship out the charge for CCD type of photodiode. This is why CCD means a charge coupling device. Now you see charge. Once we have a charge here, and you see all these devices are already coupled together, then we have a shift register, which will application of a 0 volt or 5 volt here. Then you will see through the voltage, then we can shift the charge, okay, horizontally or vertically, that's no matter, all right? Because 5 volt here means what? You have a positive here. Then negative charge will concentrate below this plate, all right? Then now we turn on this one. Now they will equally distribute here. Now we turn on this one, off all the rest. Then all the charge will appear here. Now you see the movement of the charge. Okay, so this is help you to understand. We can shift the charge, okay, by using the value inside the shift register. All right. So that is coupling the charge device. So basically, this device make use of a photodiode in this way. That means they link together, already coupled together. All right. And today you may heard of a CMOS. CMOS is to use individual photodiode separately. Then we add in 3 additional transistors. This is why we call it 3 transistor device. All right. So you can say this is a TTD. So here is a CCD photodiode. Then for CMOS, we say TTD device, all right, or TTD. But actually, the popular name is a CMOS photodiode, all right? So then we have individual photodiode. They are not coupled with the neighbor, right? And also we have a switch. So this is like a switch. This two is to one is to reset. Let me to suck out the once we finish one cycle of sensing, then we just empty all the charges. Okay, so use this transistor to do this reset. This one is to amplify the current, amplify the charges. So you see, okay, so for each sensing element with the CMOS technology, you see it's quite complicated, right? So, but the performance will be better, John, because it's individual sensing element, right? Okay. Then, okay, now we know, okay, how to convert light intensity at a single point into the voltage. Then how to convert light intensity at all point of an optic image into analog voltage. Then the answer is straightforward. Instead of a single photodiode, then you use a matrix of a photodiode, right? So now you see you have all these yellow one indicate these are the photodiode. So this is an application which make use of CMOS photodiode. So this is a CMOS photodiode, and here is a CCD photodiode. Okay, so they are coupled together. Then you see we have this vertical shift register, but later on we explain to you. All right. So once we can convert a matrix of a point of light intensity into the voltage, then output is what is a matrix of charges. The next question is how to transfer, shift out all these charges. Okay, so that is another question you will ask. Okay, and this is a real example of a CCD photodiode array. Right, so just a partial view. Then one unit is this one. So this is 1 point, this is another pixel element. Okay, the point inside the image. So now you see this is the area for photodiode, then the rest are for electronics, right? Or the shift register or whatever, right? So this is just for you to know. Okay. So before we discuss about how to shift out all the charges, let me focus on this question. Then how to capture commonness, because previously here we just talk about the intensity. Intensity is related to energy. How's about the frequency information or wavelength information, right? So then we apply this property because all incoming light could be the weighted sum of 3 primary color. So therefore, it means the incoming light we can separate these 3 primary color. How to separate red color? Then we have a red color filter. How to separate green color, we have a green color filter. How to separate blue color, then we have a blue color filter. Because the red color filter means what? Only the red component can pass through, right? Green color filter means what? Green component will pass through, right? So then in this case, one point must make use of 4 sensing elements, right? Instead of 1, because we must separately consider in the value for red component, value for blue component, the value for green component, all right? Here you may ask this question, why not to have another, because we allocate 4, okay, 4 from a square, it's easier, all right? Why not use the 4th one just to take care of the intensity? So that should be a good question. But the actual design is they use the 1st one to filter out the green color again. Actually, I do not know what's the reason. Okay, why not use the 1st one to capture intensity information? All right, then in this way, so you have a better image sensor, right? So this is my thinking, all right? Okay, but anyway, we follow the design solution made by the inventor of the CCD image sensor or CMOS image sensor, because we just purchase their product, then we just use it and then follow their design guideline. Okay, so the current design guideline is okay, 2 of photodiode are dedicated for green color component, 1 dedicated to blue color component, and 1 dedicated to red color component, right? So this current practice, and you can always ask this question, why not allocate this one to intensity sensing, right? So then we will have a perfect solution, right? Something like that. So this is a solution. So, and in this case, you will see, okay, we have a dedicated photodiode for red, green, blue, 3 green color. Then the output should be 3 color image, right? 3 matrix. So now this you can consider we have a 3 matrix, okay, and interlaced together. It's not superimposed together, all right? So it's interlaced 3 matrix, all right? 1 for red component, 1 for green component, 1 for blue component. So this is a interlaced, okay, matrix of image sensor, right? So this is a solution. Then you look at the color filter design like this, all right? So then this 4 to 1 image point inside the color image. This is the 2nd point. So see, these are the interlaced matrix of image sensor. So actually 3 matrices are interlaced together, all right, to have this pattern. So actually you have matrix for color image, matrix for blue image, matrix for green image, okay, something like that, all right? So now we are able to sense or to measure, okay, intensity, luminescence, all right, and from all the incoming line, okay, then result will be interlaced matrix of charges. Now next question is to track, okay, and make them to become a time function of a voltage in CV. Because once we have a time function of a voltage in CV, then we can send it to the microcontroller or other digital analog to digital conversion circuit, right? Then the common solution is ship the charges row by row, then column by column. That means here you see we have multiple vertical shift register. So these are the vertical shift register. You see vertical shift register, vertical shift register. Then single horizontal shift register. So that means we shift 1 row downward. Then the 1 row will receive by the horizontal shift register. Then we shift out this row. Then send the 2nd row to the horizontal shift register. Then we shift out the 2nd row. Then send out the 3rd row to the horizontal shift register. Then we shift out the 3rd row. Okay, so this is illustrated by this one. Okay, so send the 1 row into horizontal shift register. Then we shift out all the charges like one by one. After that, then we send the second row to there, okay? And this drawing basically showing you consider this is a row, okay? Don't consider the direction in the slide, okay? So one row to the horizontal shift register, then shift out all the charges. Then second row shift to the horizontal register, then shift out the second row, all the charges, etc. All right. Then this video basically illustrates the procedure, help you to visualize about my explanation. So you see all the charges appear below. Okay, when incoming light comes in. Okay, the light comes in. Now you see all the charges, right? So now we shift out the row by row. Okay. Now reach horizontal shift register, shift out, then go to horizontal shift register, then shift out again. All right. So this is the way to shift out or convert analog image into time function of a voltage in CV. All right. And this slide help you to understand. Okay, this is a static illustration. So let's say you have a full matrix. Now we shift one row to the horizontal shift register, then shift out this charges. Then we continue this process, shift out this one, then until the entire image become empty. Then we start the second capture. Okay, so this is a way to convert analog image into time function of voltage in CV. But here, this is the background knowledge for you to know. But today, this may change, all right, because we may have directly have a digital image, a different format, etc. Because in the old day, you see the TV industry or film entertainment industry dated back eventually to last century is much earlier than the machine vision industry. So for TV industry, entertainment industry, they need to have a camera to film the film, okay, then produce the film and or TV program, etc. Then they need to have a standard, okay, industrial standard. So this is why you see NTSC, PA, PAL, SECAM. So these are the video standard, okay, adopted by the entertainment industry, TV industry, which exists much earlier than the machine vision industry. So this is why you need to know, okay? So in the early day, all the camera basically will output time function of voltage according to this standard, right? So for example, NTSC is in North American, right? So the black and white version of NTSC is RS170. So this is the black white version, okay? Then, and this just for you to know, you see, when we shift out the line by line or row by row, and then we package them differently, you see row 0, row 2, row 4, okay? Come out the half image first. Then second half is 1, 3, 5. So you have an even field, odd field. And why to do this? Because we can shorten display time, channel. Because we can display this even field first. Then the audience can see the content already. Then we just add in the second field, right? So then we shorten the display time, make the viewer feel comfortable. So this is this reason. This has nothing to do with the machine vision, with the visual intelligence, okay? It's purely for the convenience or comfort of visualizing video on the screen, all right? So because this industry was dominated by entertainment industry and the TV industry, so therefore we must know such a standard, okay, and follow their practice, all right? So then you see the time function of the voltage actually is like this, all right? So even field first, then odd field, okay? So in future, if you encounter the input of such a signal, then you know how to interpret this signal. That's it, all right? But today we may heard of MP4, AVI, WMV, this digital video format, all right? So because of today, computer industry is very powerful, all right? So a lot of video will be distributed, okay, on the digital computer platform instead of analog screen, something like that, right? So the standard change, all right? And from here also you see that to study the format of a video is a big topic already, all right? Then what is MP4, what is AVI, what is WMV? So you need to spend many hours to study the detail, all right? So this is just for you to know that such thing happens there, right? If let's say we take analog video signal as an input, then how to convert it into digital value. So actually, with this type of signal, you can directly use a microcontroller already, because the microcontroller can handle this type of signal quite easily, all right? And so after conversion, you must restore the structure of the image, which is the matrix. So therefore, we must arrange them in row by row, okay? Row 0, row 1, row 2, row 3, etc. So you see here is interlaced row, all right? So then you must pay attention. That means this row will follow by this row, then followed by this row, then followed by this row, right? Because due to this interlaced nature of visual signal, right? So this is just background knowledge for you to know. But anyway, for us, after measurement and the sensing of visual signal inside the computer, we have this two-dimensional matrix. That's it, all right? So our life is quite easier as long as we understand that, okay, digital image is a two-dimensional matrix with a certain number of a row, certain number of a column. For example, in this case, we have a 480 row and a 500 column, all right? And here is another background knowledge for you to know is about the index. In C programming language, index always start from 0 to the maximum value -1. And in MATLAB, index always start from 1 to the maximum number. So there's an offset of a 1. So this background knowledge for you to know when you do the programming, right? Okay, then this video showing you example of final result which will convert, okay, the incoming light into a digital image.
The image sensor, widely used in digital still camera, digital videos, and mobile phones everywhere. Image sensors capture light. Only a specific color is extracted using a combination of red, green, and blue color filters. These are called the three primary colors of light and generate the electrical signal. There are front side and back side illumination types, also known as FSI and BSI image sensors. BSI have predominantly been used in portable consumer application until now. Panasonic has developed a new type of image sensor, which is called Smart FSI, with a new and innovative structure. This new sensor can produce stunning images in a low-light environment and yet still maintain high sensitivity, low noise, and excellent picture quality. Creating true colors and uniform brightness is a Smart FSI image sensor. Panasonic has developed a unique image sensor structure with the Smart FSI, offering high sensitivity, low noise, and outstanding image quality. A cleverly designed light separation wall and light pipe technology allows the collection of light without any loss within the photodiode. Within BSI sensor technology, loss of light is generated in the photodiode, thus creating color mixture and light inefficiency. In the case of Smart FSI, the light separation wall surrounding the pixel works as a reflector and forces the uniform light into the photodiode. As a result, it demonstrates strong color reproductivity and super sensitivity. For example, when shooting in dark surroundings, there is need to use a higher sensitivity setting, but this will cause an increase in the noise level. Smart FSI can achieve both high sensitivity and noise reduction, which enables very high color reproductive results. Light enters the sensor at different angles. The combination of light separation wall and light pipe technology allows the maximum amount of light to be captured. Because there is no mixing of colors, the outcome is a very high resolution picture. The wide incident angle characteristics can improve the image uniformity further. This prevents color shading between the center and surrounding image, and so colors are more even. Furthermore, a wider incident angle can shorten the distance between the lens and image sensor, thus enabling camera modules to become thinner. Panasonic can deliver leading-edge know-how, producing high-quality pictures even in low-light conditions. The Smart FSI image sensor, ideal for camera module prep, taking camera technology to another level.
All right. So, and in this video and in my previous slide, you also see the presence of a micro lens. Actually, micro lens is just to increase the capture of incoming light. Okay, just to increase the level of energy. Okay, in terms of intensity. So that's it. Okay, so fundamentally, we have not changed the working principle. All right, so it's good to add the micro lens there so that the level of light, okay, captured by each photo diode will be increased. All right, so that's for that purpose. All right. Okay, so that's about the study of the physical principle behind the design of a measurement of the sensor system for visual signal, right? Now, you may want to do some practice then to see how it looks like, etc. Actually, the good news is with MATLAB and your laptop PC or desktop PC, you have a camera system because all the laptop or desktop may include a webcam. So therefore, you can use a webcam to do experiment or to see how to capture image, like etc. All right. And on top of that, I guess every one of you has a smartphone or Android phone. We can turn Android phone into IP camera with the software of MATLAB. So that is also another good news for you to know. All right. So here I'm going to give you some example program for you to do the practice at home. All right. First, install your MATLAB. Then install the camera interface by following the explanation from this YouTube video, because you need to install the hardware support package for webcam and the IP cam. IP cam is for you to turn your Android phone into IP camera, right? So you just need to do this additional installation, all right? So then this is a working example, so you can copy this one into your MATLAB, then you can play with it. So basically, you should be able to see something like this. Okay, so this is a program running on my computer, right? So you can verify how many webcam inside my computer. So actually, it's two because my laptop has a front camera and a rear camera, all right? So then you can choose one or two, up to you, okay? So this is just to capture 10 image and write into the folder, okay? And do little bit of processing, convert RGB into intensity. Then you will see all these image appear here, okay? Because before the start, there's no such image there, right? So you follow this example, and then you know how to capture image, how to do little bit of processing, how to store the image, okay? So it's good enough already, all right? Second practice is for you to turn your IP camera or your Android phone into IP camera, right? So you remember launch this IP webcam application, then click Start Server. Then in your smartphone, you will see this address appear. Then you copy this address here, replace this one, because this is from my handphone, right? So then you use your one, okay? So you launch IP webcam, you can download these apps, all right? So then subsequently, you can, the image captured by your handphone will all go into your MATLAB program, okay? So you do this, okay? So then you will see what's happening. this is my intro. So here we do age detection already. So this is the image processor making use of a library function provided by MATLAB. All right. So you see, okay, so this is a result. Image come from my handphone, okay, not from my laptop, right? Because I handphone toward the laptop, right? What you see is from my laptop. So okay, so it's quite interesting. And store the image here, capture the image on the screen, right? Then third practice is for you to know, let's say, what happens if I do not have a webcam, I do not have a smartphone. Then don't worry, because from the internet, you can download a color image channel. Then you can read the image from file. Then this is an example of showing you how to read image from file, right? So then in this case, this is to form the file name. If let's say you follow this example, the file name will be the same, right? Stored inside the disk. Then eventually you can read all these file name. Otherwise, you just key in the exact name here. Okay, so this is to create the name. All right. So once your name is, you see, image read just load in the gradient, do whatever you want. All right. So then this is a small demonstration. Because in my hard disk, you see, I have 10 images like this, 1 to 10 web image, index I, so you vary. Okay, then .jpg, okay. Then you see, it process all these 10 images, right? Then result is showing here, okay. There is a loop over this 10 image, right? So every image calculate age detection, right? So, all right, okay. So once you know how to capture image, okay, then you may want to know how to process this image. Answer is to attend MA4822. All right, because to do image processing, you need to at least spend another semester. All right, okay. Do we need to do? Why do you want to do image processing? Basically, you may have some application such as visual inspection to find out whether the product is good or no good. Visual inspection, and eventually you may want to do the traffic monitoring or calculate what is the traffic volume in the street, etc. All right. So you have a lot of application in mind, okay, which will motivate you to do image processing. All right. Okay, so that's all for the study of this lecture. So key takeaway from this lecture is for you to know the physics behind visual signal, and also for you to know that you can compute two types of information from visual signal. One is related to geometry, and the other is related to color and intensity, right? And for the computation of a geometry from a visual signal, we are going to spend another 2 lectures to understand the detail, right? And for the design of a measurement and the sensing system, you know, okay, we just follow a common popular principle, which imitate the design of a human eye, all right? Then we just need to add in 3 additional modules and combine them together with the microcontroller. We should be able to come out the measurement and the sensing system for visual signal, right? The additional knowledge or information for you to know is to practice with these 3 example program provided at the end of this lecture. All right. Thank you for your attention. I'm looking forward to seeing you in the study of next lecture.